Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the question of the nth Fibonacci. This is a very famous question. Basically, you have to write a function that takes in an integer n and returns the nth Fibonacci number in the Fibonacci sequence. So, in case you're not aware, the Fibonacci sequence is a very famous sequence of numbers in math. The way that it's defined is the first two numbers are 0 and 1. They're kind of just given to you. And then every number thereafter can be found by adding the two previous numbers. So here you can see that this 1 is equal to 0 plus 1. This 2 is equal to 1 plus 1, and so on and so forth. This 21 here, for instance, is equal to 8 plus 13. So the actual math formula can be written as, for n greater than 2, fib of n is going to be equal to fib of n minus 1 plus fib of n minus 2 for n greater than 2. And that's kind of the math formula. Whoops, let me just rewrite this here. All right. So how do we solve this using programming? How do we kind of write an algorithm or come up with an algorithm to solve this? Well, believe it or not, there are quite a few ways to solve this algorithmically. We're going to be covering 3 different ways and really diving into their differences in space-time complexity analysis. But so let's start with a recursive solution. And you'll soon notice that this recursive solution that we're going to write is going to be very, very similar to this sort of math formula here that we wrote, the sort of definition of a Fibonacci number. But so basically what we can write is if n is equal to 2, then we return, we return 1, which is this number here, right? We were told that the second number in the Fibonacci sequence is always 1. Then if n is equal to 1, then we return 0, because we know that the first number in the Fibonacci sequence is always 0. So these here are both of our base cases in our recursive algorithm. And then we can say else return, and here we can literally return our math formula. So we can return fib of n minus 1 plus fib of n minus 2. And this entire thing here can be our fib function, which just takes in an integer n. And that's literally the first solution, right? You have your 2 base cases, and then if you don't hit those base cases, you call fib of n minus 1 plus fib of n minus 2. And so if we were to go through an example, let's say we had fib of 4. So fib of 4, the answer for fib of 4 is 2. We would call fib of 4. 4 is not equal to 2 and it's not equal to 1, so we wouldn't hit either of the base cases. So we would call return fib of n minus 1, which would be 3, plus fib of n minus 2, which would be 2. For both of them, for fib of 2 here, we would hit the base case, which would be 1. And for fib of 3, we'd have to recall the function, and we wouldn't hit the base case because 3 is bigger than 2 and 1. So we'd get into this else statement, and we'd say return fib of 3 minus 1, which is 2, plus fib of 3 minus 2, which is 1. And both of these would hit the base case, so we'd have 1 plus 0 plus 1 from the first call, and we'd be done. And we'd get the answer 2. So that's kind of the first, I kind of want to call it naive way of solving this problem recursively. Why is it naive? Because the time complexity analysis of this algorithm isn't great. We'll dive into the space complexity in a second, but the time complexity isn't great because if we really think about it, we are doing a bunch of unnecessary calculations here. So let me actually let me erase this entire math formula here in the middle, and we're going to go through an actual example to see what gets called, how many times, what functions get called, etc. So let me move our Fibonacci sequence to the top right here, and let me move our actual answer to the top. And so let's say we had fib of 6. So if we have fib of 6 is going to end up calling fib of 5 and fib of 4, right? Because we're not going to hit any of the two base cases with fib of 6. So we're going to call fib of 6 minus 1, which is fib of 5, fib of 6 minus 2, which is fib of 4. And then the fib of 5 is going to call fib of 4 and fib of 3. And fib of 4 is going to call fib of 3 and fib of 2. And already here we can see that we're repeating a bunch of computations. We have fib of 6 that calculates fib of 5, and fib of 5 calculates fib of 4, calls fib of 4, but then we're going to have to call fib of 4 again up here, and then fib of 5 also calls fib of 3, which is going to have to be calculated again here, and this goes on, a bunch of times until we hit the base cases. So not only are we doing all these kind of duplicate or even more than duplicate calculations, but basically at each call of the Fibonacci function, we're doing 2 additional calls to the Fibonacci function. So at fib of 6, we're doing fib of 5, fib of 4. At fib of 5, we're doing fib of 4, fib of 3. At fib of 4, we're doing fib of 3, fib of 2. Here, in this fib of 4, at the bottom left here, we can do 2 other calls to fib of 3 and fib of 2, and so on and so forth. So what does that result in terms of time complexity? Well, it's going to be a time complexity of 2 to the power of n. So let me write that down, and let's just explain why that is 2 to the power of n. Why is it 2 to the power of n? Well, we start at fib of 6, which is our n, right? And we go all the way down to fib of 1. And at each of these fibs, we call 2 more fibs. So fib of 6 calls 2 more fibs. And then each of these 2 fibs call another 2 fibs. And then each of those call another 2 fibs. So basically every time we're doing 2 times 2 times 2 times 2, and then n times. We're doing that n times, or almost n times. So it converges to 2 of n time. So that's the time complexity. And because we saw that there are a lot of duplicate computations, that tells us that this can probably be done a lot more optimally. And probably we can get a better time complexity. But before we move on to another solution and a better one, let's dive into the space complexity analysis of this. So the space complexity analysis is actually going to be O of n. And you might be wondering, let me write here, this is going to be O of 2 to the n. Forgot to write the O of 2 to the power of n. For the space complexity, it's going to be O of n. But why is it going to be O of n? You might be wondering or thinking, wait, we're not storing anything, right? At no point in our function here are we storing things in an array or in an object or something like that. So why do we have space complexity? But you have to remember, this is a recursive function, right? So we're going to be using kind of the function call stack a lot, and it's going to be using up memory. So if we have here, let's like try to draw out the call stack here as a bucket, and we have a bunch of like frames on the call stack, right? When we call fib of 6, fib of 6 starts to run, right? And so we can put here fib of 6 on the call stack at the very bottom of the call stack. And then fib of 6 calls fib of 5 and fib of 4. Before it even calls fib of 4, it calls fib of 5, right? There's an order to this, and it starts with fib of 5. So then fib of 5 kind of goes on the call stack here. And then fib of 5 calls fib of 4 and fib of 3. But, at the beginning, it calls fib of 4. So fib of 4 goes on the call stack. And so, like, fib of 6 and fib of 5, which are on the call stack, they're just kind of hanging there in memory. And they're saying, we're waiting to get the response of the fibs above us, right? And until we get that response, we have to be kind of stored in memory to remember the state that we're in. And this goes on until we hit our base case, right? We're going to store fib of 3. We're going to store fib of 2. And I think at fib of 2, we're going to be done, because at fib of 2, we're going to hit our base case. And so once we hit fib of 2, we can kind of erase fib of 2, then erase fib of 3, then erase fib of 4, then erase fib of 5, and then erase fib of 6. Because we kind of go back up the call stack. But so, and this is done, mind you, this is done like twice over. We might not actually erase in this order, because like by the time, like when we let me undo this for a second. We'd erase fib of 2, and then fib of 3 would now call fib of 1, right? After we get fib of 2 for fib of 3, we call fib of 1. And then we can erase fib of 1. And then we can erase fib of 3. And now fib of 4 calls fib of 2, right? So each function kind of calls 2 different fibs. But eventually, we can erase them all and go back all the way up the call stack. The point is, during a given, like, during the entire kind of algorithm, right? The entire algorithm's lifespan, we have at most on the call stack n function calls. Beyond that, we start hitting base cases and we start kind of clearing up the call stack. But so, because we have at most n frames on that call stack, at any given time in the algorithm, we are storing at most O of n space on that call stack. And so that's where this space complexity comes from. So that's the the space-time complexity analysis of this first recursive solution. Now, as I mentioned, there are a few different solutions, and the second one we're going to cover is going to also be recursive, but it's going to make use of something called memoization, in other words, caching, to solve this a lot more optimally. So let's erase this call stack, and let's grab this entire Fibonacci tree that we wrote here, and let's make it a lot smaller. We'll remember that in this tree we had a lot of duplicate calculations. We calculated, fib of 4 twice, fib of 3 like a bunch of times, etc. So what if we could store all these solutions that we calculate, like fib of 4, store them in some kind of object or hash table, and then access them in constant time, in O of 1 time, in the future. So in other words, we could say, like, if n is in memwise, let's call our sort of caching hash table memwise. If n is in memwise, just return memwise of n. So if we have our solution to a given Fibonacci function for a given n stored in memwise, return memwise. Otherwise, else, we store in memwise of n, we store the formula that we had written for our solution above. So we say memwise of n is going to be equal to fib of n minus 1 plus fib of n minus 2. And then we say return memwise of n. So what's happening in this function? Here, we're storing things in this memwise hash table, and then we're returning them, and then whenever we encounter, the same n being called, it's going to be in memwise, and we just access it in constant time. So if we go back to our example with fib of 6, we're going to start with fib of 6. Fib of 6 is then going to calculate fib of 5, which is then going to calculate fib of 4, then 3, then 2, and 2 is going to be in our memwise hash table. So then fib of 3 is going to calculate fib of 1, and 1 is also going to be in our memwise hash table. So let's write the values that are in our memwise hash table in a different color. Let's write them in brown. So 2 and 1, these are kind of constant time operations because they're stored in our hash table. So because we have those two, we get the solution for fib of 3. So now we can store fib of 3 in our hash table. Then fib of 4 is going to call fib of 2 as well, right? After we've gotten fib of 3, we call fib of 2. But fib of 2 is in our hash table. So we can write it in brown, and it's a constant time operation. So now we can erase fib of 4 and put it in brown because it's stored in our hash table. We can store it. So then fib of 5 is going to call fib of 3, but fib of 3 is just a constant time operation now because we've stored it in our hash table. So like everything that comes after fib of 3, which was a bunch of stuff here, we can avoid now here because 3 is stored in the hash table. So now we can erase fib of 5 and put it in brown because it's stored in our hash table. And lastly, our fib of 6 now calls fib of 5, but fib of 5 is stored in our hash table because we just calculated it. So we can erase fib of 5 and put it in brown, and this entire sort of part of the Fibonacci tree here is just going to be constant time. We just access it from our hash table. Okay? And so this algorithm is not going to run in O of 2 to the power of n time. It's going to run in O of n time. Why does it run in O of n time? Well, we're going to calculate every Fibonacci number once, right? Because Fibonacci of 6 has to calculate Fibonacci of 5, which has to calculate Fibonacci of 4, which has to calculate Fibonacci of 3, which has to calculate Fibonacci of 2, and then we're done. Once we've calculated, once we get to Fibonacci of 2, which is in our hash table, and Fibonacci of 1, which is in our hash table, we then get the answer for fib of 3, stored in the hash table, which then gives us the answer to fib of 4, which we store in the hash table, and so on and so forth. And then any other computations, we just access from the hash table, and they're just like constant time. So in total, all we're doing is calculating each Fibonacci number, the n Fibonacci numbers, once, and every sort of second call to the Fibonacci function that they do is just a constant time operation because that value gets stored in the hash table. And so that leads us to a time complexity of O of n time. And then the space complexity is going to remain O of n because two things. One, we still have that call stack issue with the recursion because we're using a recursive function. We have to we have frames on the call stack being used and stored. And on top of that, we have this Memoize hash table, right? That we are just that we're using to store values, right? To store answers, and we're going to be storing n answers. So, then space. All right, can we do better? Is there like a better way to solve this? Yes, there is. I mentioned that we were going to cover an iterative solution. So the iterative solution is the best one by far because basically it's going to eliminate using any kind of space. Okay. What we're going to do is we're going to have an array of the last two Fibonacci numbers. And this doesn't need to be an array. This could be like two variables or an object. It doesn't really matter. Point is, we store the last two Fibonacci numbers. And we initialize, here I'm going to go with an array. We initialize this array to have the first two Fibonacci numbers. So 0 and 1. These are the first two Fibonacci numbers from our sequence, right? And so then we start calculating every Fibonacci number thereafter. So, let's say we have fib of 6. So n is equal to 6. We say while we keep track of how many calculations we've done, how many new Fibonacci numbers we've calculated through some kind of counter. And we say while the counter is less than or equal to n, just keep calculating the next Fibonacci number. And the next Fibonacci number, let's call it next here, next is going to be equal to this plus this. So here, it's going to be equal to 0 plus 1, which is going to be equal to 1. So what do we do when we've calculated next? Well, we take the first number in the array and we just get rid of it. We just throw it in the garbage can. We take the second number and we put it back. We put it in the first place in the array. And we get our new Fibonacci number and we put it in the second place in the array. And so now we can calculate the next Fibonacci number. And the next one is going to be equal to 1 plus 1, which is going to be equal to 2. And so here we take this number and we get rid of it. We move this number to the left and we grab our 2 and we move it in the array. So basically, at any given time, we're only storing two values, the previous two Fibonacci numbers. We calculate the next Fibonacci number in constant time by just accessing these two values that we're storing. And then we just update the array. So now here we're going to have 1 plus 2. And we're going to, take this 1 and put it in the garbage disposal. Take this 2 and move it here. And then 1 plus 2 is equal to 3. And we take the 3 and we move it to the top. And so this is going to run in the same time. It's going to run in O of n time. So time is going to be O of n because we have to calculate n Fibonacci numbers, right? So we have to do at least n constant time operations. But the space complexity is going to be O of 1 because we're literally not using space. We're not doing any recursive calls, so we don't have to worry about the call stack. And we're not storing anything except for two values, which is just, constant space. And we're done. Once we've calculated n Fibonacci numbers, we have our solution, and we can just return whatever value is stored in the second spot in the array. So that's it for the conceptual overview of the nth Fibonacci function. There are a lot of different ways to solve it, as we saw. Some are better than others. But so let's dive into the code implementation to see what it looks like. All right, so we've got our get nth fib function defined. It takes in an integer n, and we're going to start with that sort of naive recursive solution that we came up with earlier. So the first thing we're going to want to cover is our base case, or rather our base cases. So if n is equal to 2, we want to return 1. elif n is equal to 1, we want to return 0. Those are the two first Fibonacci numbers that we know kind of right off the bat. And then otherwise, if we don't hit either of these base cases, we can just return get nth fib of n minus 1 plus get nth fib of n minus 2. That's kind of our general math formula, the way the Fibonacci sequence is defined. And so this solution is going to run in O of 2 to the power of n time and O of n space, because we are doing all these recursive calls and we're using up frames on the call stack. So now let's cover the second solution, which was also recursive, but which used this idea of caching or memoization. So we can add in a second argument to this get nth fib function, which is going to be our memoize hash table. And this memoize hash table, we can initialize it here to be an object, right, or a dictionary in Python that has 1 which points to 0 and 2 which points to 1. That's kind of those are the two base cases that we immediately store in our memoize hash table. And then we can say if n is in memoize, just return memoize of n, right? If we already have the answer stored, return it. Otherwise, memoize of n is going to be equal to get nth fib. This is where we do the recursive calls. Get nth fib of n minus 1 and memoize. You pass in that memoize object, plus get nth fib of n minus 2 and memoize. And then you just return memoize of n, whatever we just calculated. So again, we have our get nth fib. When we call it at the very beginning, like get nth fib 6, we initialize this memoize hash table to hold the sort of two base cases. And then we say if n is in memoize, return memoize of n. Otherwise, calculate memoize of n, calculate the value of that we're looking for by calling our math formula, passing in this memoize hash table, and then return memoize of n. So this is going to run in O of n time, because we're not doing any of these duplicate calculations, but it's still going to run in O of n space. And so lastly, we can come up with our iterative solution. So the iterative solution is going to be pretty different. It's just going to take in a number n, and we're going to go with this array approach where we store the last two Fibonacci numbers in an array. So we're going to say last 2 is going to be equal to 0, 1. We initialize it to our base case. And then the way I like to do this is having a counter. So we can say counter is going to be equal to 3. In other words, we've got 1, 2 Fibonacci numbers right now, and now we're about to calculate the third one. And so we can say while counter is less than or equal to n, we calculate the next Fibonacci number. So if we had called get nth fib of 3, well, our counter would be less than or equal to n, which is 3. So we'd calculate the next fib. Next fib is going to be equal to last 2, 0 plus last 2, 1, right? The sum of last 2. And then we say last 2, 0 equals last 2, 1. Here we kind of threw the first value in last 2 into the garbage and moved the second value of last 2 into the first place. Then we say last 2 of 0, or of 1, sorry, is going to be equal to next fib. And lastly, we update our counter, right? Counter plus or equals to 1. And that's it. We keep doing this while loop until finally our counter goes above n. And we're done. We've calculated n Fibonacci numbers. And so now we can say return last 2 of 1. Now here there's just one little edge case that we have to take care of. If we had called get nth fib of 1, right? Imagine we wanted the first Fibonacci number. That would be the only case where we don't want to return last two of 1. We want to return last two of 0, right? The first value in last two. So here we can say return last two of 1 if n is greater than 1, else, else return last two of 0. That's kind of just a simple ternary operator here to take care of this edge case. But so this algorithm, this iterative solution, is going to run in O of n time, but in only O of 1 space, because we're not storing anything apart from the last two Fibonacci numbers. All right, so that's it for this problem. I hope that this video was helpful. I hope that it taught you a lot about kind of the differences between recursive algorithms, iterative algorithms, recursive algorithms using memoization or caching versus those not using that. And I'll see you in the next video.